Okay. Today's topic of my presentation is enhancement of harvesting capability of coupled nonlinear harvesters. So myself, Dr. Pradeep V Malaji, Department of Mechanical Engineering from BLDEA's VP Dr. Halakatti College of Engineering and Technology, Vijayapur, Karnataka, India. Okay, nowadays we are talking a lot of things like IoT system and structural health monitoring, all these things. The main component of these things, just a minute, I will take this. The main component is we need a lot of wireless sensors, and the problem here is how to power them. So we'll be just discussing one of the solutions. So how to power these wireless sensor nodes. So this will be flow of my presentation today. So we'll just start with introduction to energy harvesting. So which can be one of the solution to power of these wireless sensor nodes. Then we'll have just quick glance of what this energy harvesting system is and what are different, what is the limitation of energy harvesting system. Then we'll move on to the coupled harvesters. So we'll come on to our proposed harvester. We'll discuss some results on that. So finally, we'll conclude with summary. So coming out of the introduction to energy harvesting, so most of us know. So we have a lot of surroundings which are like radio frequency, energy, vibration, solar, thermal. So these things we can convert into useful electrical energy. So via some generator, so these can be either stored or can be directly used for the electronic devices, or it can be stored and used in later stage. So where it is applicable and why we should go for this one. So as we discussed previously for IoT system and structural monitoring, a lot of wireless sensor nodes. So some of these electronic devices, they need power input in terms of nanowatts to microwatts. And in our system, what we are discussing, so we'll be getting power in terms of this nano to microwatt level. So we can power up these things. So this can eliminate use of lithium batteries, which are hazardous, and it will be maintenance free and ease of accessibility where we are not able to access the things. There we can utilize this harvesting system. It has a lot of applications like biomedical, wireless, and structural health monitoring. So quick glance, what exactly vibration energy harvesting is. We are now coming particularly to vibration energy harvesting, where our discussion belongs to. So available vibration sources we can convert into energy harvesting. It can be stored and then can be supplied to the devices. So we know there are three methods by which we can convert vibration into electrical energy. So electromagnetic, piezoelectric, and magnetostatic. So today's our talk will be mostly on this electromagnetic energy harvesting. So coming on to linear harvesters, so we know single degree of freedom system, swing mass system. So that same system can be used. So it started with Williams et al. In 1995. They just took a simple spring mass system model, where they simply said that so energy lost can be converted into the electrical energy. So here if you take a simple electromagnetic system, so this is a well-known equation for all of us for the spring mass system, and from that we can harvest energy, so voltage, which can be given in terms of electromagnetic flux and length of coil and velocity of the mass. So and we can write power in terms of velocity, voltage and the resistance. So one of the disadvantages with linear harvesting, like we know that linear system, it has its peak at resonance. So at all other points, so we will be getting less power. So this is what excited a lot of researchers to go further and do research and exploit. So what other things are there to increase the energy harvesting capability? So at current, the challenges that we are facing, so with this conventional harvester is that single frequency harvester, like we can generate only at a particular frequency, in general at resonance. So we don't have many of the harvesters which can harvest power at the low frequency, and also we have limitation to the bandwidth. We are not able to harvest for the larger band. So we need to address these problems. So a lot of researchers are uh, thinking of different ways, the different harvesters have been designed. So we'll be discussing a few of them, and in particular to the coupled system. So at present we have following solutions. So in order to have broadband energy harvesting, one of them is multimode or array of linear harvesters. Here we use coupled harvester or set of harvesters with different properties which can harvest energy at different frequencies, and we can get a broader bandwidth. Or we have one more option, we can go for nonlinear harvesters, which because of spring hardening or softening, we can harvest frequency for the wider bandwidth. So third option is it's more relevant to the electronics network circuit system. So we'll be limiting our discussion today to first and second, multimode and nonlinear harvesters. So we'll be mixing these two things. So what will happen? We have multiple nonlinear harvesters and coupled system. So coming on to the coupled harvesters in particular, so a lot of researchers have proposed the system with coupling. Like in 2009, Ang proposed one of the system where two beam with N mass have been coupled by a spring. So effect of this spring is that like these two independent harvesters, when they connected by spring, they got converted into 2 degrees of freedom system. So due to which, so we can harvest power at two different frequencies because of 2 degrees of freedom system. So they have shown what is the effect of coupling on this system. So this mass 1 and mass 2 are different; they are not same. So these are two different systems with different parameters. So with increase in coupling, so we can observe that there is an increase in harvested power, but at the same time there is a reduction in the bandwidth. So we need to select an particular optimal value of stiffness where we can get the larger bandwidth. Continued on the same concept, we along with myself along with Dr. Ali from IIT Madras, we conducted what happens if we have a number of harvesters connected together. So does it mean that if you connect multiple harvesters and number of harvesters will keep on adding power or keep on adding bandwidth? So what we found that, so there is a saturation point after which if we keep on adding number of harvesters, it will not help us either in getting maximum power nor in getting maximum bandwidth. So that saturation point depends upon the parameters we selected. So increment in the length. So what we found that after certain value of numbers, there is no use of increasing the numbers. So bandwidth cannot increase beyond that value. But these two systems where we consider, they just talked about total power output. So we need to investigate what happens at the individual harvester level. So which one is contributing more and which one is contributing less. Then researchers, they took magnetic coupling between harvesters and they analyzed what will happen with individual harvester. In 2015, Ju and others, what they did is they took two different beams with end magnets. These masses are magnets, and there is an interaction between these two magnets. So due to which there is a magnetic coupling between them. So here, one of the harvester has different mass compared to other one, or different length in turn also. So with the harvester which has the lowest frequency, you can see here in the figure A here, so it can produce maximum voltage, and the one which has high frequency, it produces a lesser voltage compared to the other harvester. Similarly, so we can see a lot of research. So what they have done is like, if you are getting less power from one of the harvester, like for example high frequency harvester, so why no need to go for that harvester, like we can use that as a just oscillator. So Tang and Wang in 2012 and Zakaria and recently in 2019, what they proposed that, so if one of the harvester is giving less power, so then why to waste material on that one? So what we can do is, what they did is, they just took one of the harvester as oscillator, and low frequency harvester, they harvested power from the low frequency oscillator. So because of which they can harvest maximum power from the low frequency harvester. So these are the outcomes from the previous literature. So one is contribution from low frequency harvester is more, whereas high frequency harvester contribution is very less compared to the low frequency harvester. Then, so in to solve the like to overcome these things, some of the researchers suggested that okay, you can use only the low frequency harvester for harvesting. Other one can be used as the oscillator. So to in order to save the material, I request everyone to mute themselves. I'm getting a lot of noise. Okay. No, but so what is the problem here? Like, what about energy density? Like, we are utilizing a lot of space here, but with reduced density. So, is there any way so that we can increase our energy harvesting capability of both the harvesters? So, in order to, in that way, in 2017, myself and Dr. Ali, we suggested one of the option. So, coupling like nonlinear magnetic as well as mechanical coupling. So here you can see that there is a magnetic interaction between these two pendulums as well as magnetic coupling between these two pendulums. So there is presence of both magnetic as well as mechanical coupling here. What is effect of this one? So previously in previous cases, either there was a mechanical coupling or there was a magnetic coupling. Because of magnetic coupling, there was initial energy input. It showed that if we use both magnetic and mechanical coupling, we can enhance the harvesting capability of both harvester, low frequency as well as high frequency harvester. This has advantage over previous research that so we can use both harvesters and we can improve the energy density or power density of the harvesting system. This dotted line represents bandwidth of second pendulum, so that is which known as low frequency pendulum, and this continuous line blue line is for the pendulum 1. So we divided this into 3 zones, zone 1 and zone 3. So here what we can get is total power. So we can use both harvesters to get the maximum bandwidth. But particularly here, if you see in zone 2, here pendulum 2 is dominating pendulum 1. Most of the bandwidth is contributed by the pendulum 2. Pendulum 1 is its participation is almost negligible. Pendulum 2 can give at particular value of 0.9 of the coupling value. It can give as good as total bandwidth. So in this scenario, it is suggested that whatever the previous literature have shown that you should utilize another pendulum as just oscillator. No need to go for the both harvesting from both pendulums in order to save the material. But if you are in zone 1 or zone 3, then that oscillator system is not suggestible. We can use both. But still, is there any, we are introducing coupling here, and these are just numerical study and we have done experimental. So we are getting multiple solutions here. In order to study like what are the different solutions we are getting and what are the different dynamics that we can get. So we did an harmonic balance analysis and compared with the numerical value, numerical study. Here when coupling is 0, so pendulum 1 and pendulum 2, so both numerical values as well as this harmonic balance values are similar, like we are getting same results from both the systems. When the coupling is introduced, a new phenomenon has been observed here, so, which is called as frequency island, or someone called it a frequency bubble. And detached frequency curve can be observed here in pendulum 1, which is away from this main frequency curve and which is having the higher value. If we keep on increasing coupling value, this isolated frequency curve, it keeps on moving away from the main curve. But it is not similar, it is not same for the pendulum 2. We can see that we are having isolated frequency island which is moving away from, but it has a lower amplitude or lower magnitude. This is interesting phenomena, and this can be found only when there is a coupling of the nonlinear system. You can clearly see here that when there is no coupling, there is no concept of isolated frequency islands. So this frequency island along with other solutions, so makes us to check whether we can get these all other solutions with some random initial inputs, and we can whether we can enhance the performance of the both harvesters. We can easily clearly see here that these numerical values are almost coinciding with the harmonic balance method values. At this particular frequency example at 0.8 or 0.82, numerically we are getting a low frequency solution, low amplitude solution, but at the same time if we check for the harmonic balance, we are getting total some 7 solutions, out of which 3 stable and unstable solutions are there. Is it possible to shift from this low amplitude solution to high amplitude solution, or can you reach somewhere in between? So low level, medium level and high level. So can you reach from this solution to this solution? So this needs to be checked. So to understand this and where we can reach, can you reach to the maximum or can you reach to the medium, we just checked for some basin of solution. We varied the initial condition of second pendulum and kept initial condition of first pendulum constant. So here in these figures it shows basin of solutions. This black mark indicates low amplitude solution and blue mark indicates medium solution. So we are not in this defined zone, we are not able to get we are not able to reach the high level solution, but still we are able to reach the medium level, which is not possible with the previous condition, without initial condition. So with this, if you plot for a particular value of initial condition, we can clearly see here that so with initial condition, these blue lines, we can get more current output compared to the with zero initial condition. Both pendulum 1 as well as pendulum 2, they have shown enhancement in the output, current output. But so this particular getting medium solution has been limited to low zone of initial condition. So these are the initial conditions we have to select to get the high amplitude solution. With this new initial condition, set of new initial condition, if you do the numerical calculations, what we can observe is that there is enhancement in current output of both the pendulums, pendulum 1 as well as pendulum 2. Here dW indicates bandwidth. So dW, so the hidden line, dotted line indicates with new initial conditions, and continuous blue line is for the previous one, that is with zero initial condition. So for pendulum 1, we can see there is an increment from a bandwidth of it is non-dimensional bandwidth from 0.05 to 0.17. Similarly, there is an enhancement in bandwidth of pendulum 2 from 0.11 to 0.17. So almost in pendulum 1 it is 3 times enhancement in the bandwidth, and pendulum 2 1.5 times 0.5 times increment in the bandwidth. So whereas maximum or peak power not affected in case of pendulum 1, but pendulum 2 we can also enhance the power output. Outcome is that from pendulum 1 So almost we are able to enhance 140% of the bandwidth with a proper initial condition. Whereas for pendulum 2, we can enhance and 11% in the peak power. But the question is, so these are just theoretical and numerical studies, how to achieve this. So previous literatures have shown that, so we can give some initial condition or impact. One is impact based, as suggested by Zhu and all in 2015, or we can give initial energy input by providing an magnetic interaction between pendulum, one of the pendulum, and other pendulum can be free. We are supplying extra energy to the one pendulum, and that extra energy can be transferred to the second pendulum via coupling. Or one more method is by chaos control. So these three methods can be used to attain highest or maximum possible harvesting capability from both the harvesters. So we also checked what happens inside each of the pendulum dynamics. What we observed is that, so these two can with increase in mechanical coupling ratio, these two pendulums can attain chaos, high amplitude chaos through quasi-periodic route. So it can be clearly visible here in terms of phase plots. In conclusion, if you select proper initial condition, or we can give a proper initial energy input to one of the pendulum, we are able to enhance the performance of both the harvesters, so that we can get the maximum power density. So and what we observed is, so there is a quasi-periodic route to chaos. These are the few references. So I thank you all. Like, if any questions, either you can contact me at this mail, or you can put in my message box. I should thank all these my institute, BLDEA Association, BGST, Global University of Technology, and ES Dialog, and especially Professor Litak and Peter. Thank you.
Thank you. Thank you very much for a very nice presentation. And I think that we have some maybe some time for a few questions. So maybe you have somebody has some from our audience have any questions or comments? Yeah.
At the chat window that you can see.
You can see on the chat. Yeah. This is maybe you can answer. Pradeep, you can answer some questions on the chat. Yeah. Yeah.
Okay, one of the question is whether from Christina, whether it is harmonic driving. Yeah, absolutely. Like, we consider the harmonic input. And the second question, so what is the practical application? Like, pendulums are usually known for low frequency harvesting. So we have a lot of application in areas of low frequency. Like, if you in particular we take structures which have a frequency below 5 Hz, maybe offshore structures where a frequency we need pendulum kind of structures which are advantages over other things. Another question is, adding a second pendulum worth it from a volumetric power density point of view? That's what, like, previous researchers have shown, like, in order to improve the energy harvesting capability or bandwidth, researchers have proposed multiple harvesters, and then they moved on to the coupling. So these things, volume is increased, but volumetric power density, sometimes if you are using only one pendulum or one harvester, so there is a question of volumetric density, like it will be very less. Then, so in order to enhance that, so these are the proposed things where we can increase volume power density. So these are the systems are like maybe initial energy input, and one we proposed mechanical harvesters. By these means, we can enhance the volume power density also. And next question, what is the mean value of energy that is possible to obtain from this? Okay, mean value of energy. The question is, what is the mean value of energy that is possible from this device? Okay, and the proposed device, it's just we have done the parametric analysis. The previous one, which used magnetomechanical system, we almost got 150 microwatt power output from that system. The present system, we are not yet done with a practical or experimental thing. Once we do that, we'll be able to know the exact mean value. There is one more question. What is the size or volume of these devices? Okay, at this experimental level, it's kind of big size only. Like the previous one, magnetomechanical harvester, it was around 20 centimeter wide and around 20 centimeter height. Thickness wise, very small, like around thickness wise 3 centimeters.
Okay, so I see that the questions are answered, or maybe there is one from Daniel here. So maybe we, yeah. Mm-hmm.
1 second. Okay, can you control initial condition? Yeah, that's interesting. Like one of the I think one of the reference I gave at the end, that is chaos control. So we need a closed loop control system there, but in that case again we need to supply energy to that control system. Like we need to analyze how much power we are generating and how much energy has to be supplied. That like many studies are there, like where they are able to control chaos and harvest power at the high energy orbits. It's possible, but at this present study we are not considering this. Just we are focusing on impact or magnetic interaction. Yeah, exactly. One more question. Theoretical point of view, but in practice they are not harmonic tuned. Exactly. So many of the actual applications will not be having harmonic input. It will be like random input. So in that case, previous studies have suggested that if you have multiple harvesters, so they are best performing under random conditions. And in previous study, we found that even with random inputs, we are able to harvest a fair amount of power. And there is a lot of literature available. So we suggested that multiple harvesters are capable enough under random input also.
Yeah. Okay. So I think that this is maybe these are all the questions you answered, and I would like to tell that maybe these chaotic solutions really could be interesting to control these kind of solutions, and as you mentioned that. This is very also these chaotic solutions have a large amplitude response. So this is good to have such a solution because it has finally large amplitude, and but it's probably difficult to control the chaotic solutions. Yeah. So this is another problem, and. But I see that there are some new questions. Maybe you can tell.
Yeah.
To the questions, you can respond to the questions. Yeah.
Is it possible to tune this device automatically during its work to obtain the best conditions of work whole in and exactly like that's what previous question was, like can we control it? So that's all about chaos control. So So if you go for chaos control, it's kind of automatic only. Again, that question remains there. So how much energy is required for that controlling and how much energy we are harvesting? So that's again a challenging area to work here.
Okay.
I think there is one more question. How do you match the load to this behavior? Okay, it's a normal magnetic electromagnetic harvesting. So in this case, usually we are matching external resistance with the resistance of the coil. Okay, any more questions?
I can't see very more questions. Yeah.
Yeah.
So thank you very much, Pradeep, for this nice presentation. And I think that if you still, if all the people, participants have some more questions, can send an email to you, and you can also discuss some details.